Hello everyone and welcome to my project presentation on an automatic garden watering control system using a PLD controller in MATLAB and Simulink.
And these are our group members.
Maintaining the light moisture level in soil is critical for healthy plant growth. In many gardens, this is done manually, which can be inefficient or inconsistent. To address this, we implement a feedback control system that uses soil moisture data to automatically regulate water flow, just like a thermostat controls room temperature. We begin by modeling the soil as a first-order system, where the input is the amount of water added, and the output is the resulting soil moisture percentage. The relationship is defined by a transfer function Gs equals 0.8 divided by 30s plus 1. This models the system's dynamics with a gain of 0.8 and a time constant of 30 seconds.
Input and output. In this system, the input is the water control signal on and off of flow rate. The output is the measured soil moisture, and the system has a natural delay due to absorption characteristic. Time domain analysis. Next, we analyze the step response of the system, which show how the soil moisture rises over time in response to a sudden watering command. We can see that it rises slowly and eventually stabilizes. This is typical of a first-order system. Frequency domain analysis. To understand how our system reacts to different frequency or environmental change, we also examine the Bone and Nyquist plot. This helps us assess system stability and controller design requirements.
Hello. So now we will explore the design simulation and performance analysis of an automatic garden watering control system using MATLAB. This we will walk through the system modeling, controller design, simulation result, and real-world applications. And these are the codes we are gonna talk about. First, we model the soil moisture response as a first-order system. This is done using transfer function Gs equal K divided by Ts plus 1, where K is equal 0.8 is the gain, and T is equal 30 seconds is the time constant. It reflects how moisture increases in the soil after applying water. This is what we define in the MATLAB. This input is the water flow rate, and the output is the soil moisture level in a percentage. Next, we analyze the system behavior in both time and frequency domain. First, we use a step response to observe how soil moisture changes over time when the water is suddenly applied. The graph shows gradual rise, typical of a first-order system. We then move to frequency domain analysis using Bode and Nyquist plots. The Bode plot show gain and phase margins useful for evaluating system stability and responsiveness. And the Nyquist plot helps visualize stability in margins in the complex frequency plane. These plots help us to understand how the system responds across different frequencies. For our controller design, we design and compare three classical controllers, PI, PD, and PID. Each controller was manually tuned based on the system response. As you can see, the KP is 1.2 and the KI is 0.1 for the PI controller. And for the PD and PID, we also tune it manually. You can see on the code. The PI controller improves steady state accuracy. The PD controller boosts speed and reduces overshoot but doesn't correct the steady state error. And the PID controller combines the best of both fast response and accurate tracking. These controllers were applied in a feedback loop below. After implementing the controllers, we simulate their step response. All three were plotted together to compare how they affected on the system behavior. As you can see from the graph, the PID controller offered the most balanced performance, fast rise time, low overshoot, and quick settling time. And we also extract this metric using MATLAB step info function. And we got these performance metrics on the bottom right of the code.